Hello everyone and welcome back to a new session for Computer Science 2 for the summer semester 2022. Today we are at chapter 20, Recursion. So as usual, I have the book next to me. I'm on page 1223. First, what is recursion? To define it, recursion. So recursion or recursive functions, basically. So recursive functions are functions that call themselves. So you know how you have sometimes chain of functions. You have function A that calls function B, then B calls function C, etc. Sometimes with recursion, you have functions that call themselves. You have direct recursion and you have indirect recursion. Direct recursion is basically A calling A, then calling A, then calling A. It repeats itself. You can think about it as a loop. It's a loop. A, I want to run the same task 5 times. The task would be in a function, and then first run, then the second run, the third run, fourth run, fifth run, and then I break the chain and return. Indirect recursion is when A calls B, then B calls A, then A calls B again, then A calls B, etc. This is indirect. You can add as many as you want, ABC, then ABC, then ABC. They follow the same concept, indirect recursion and direct recursion. Let's do a quick example. For example, I'm going to have a function called void. It doesn't return anything. I'm going to call it display. And it takes some integer, int a number of times. I'm going to run this function x number of times. Inside it, first, in any recursion function, you need a base case. And then you need the task. The base case basically is your condition to break the chain. When will I stop? I'm going to keep calling myself, but I need to stop at some point. If I don't stop at any point, then it's an infinite call. Infinite calls of A, if I don't stop. So in this example, my base case would be if A number of times is above 0. As long as this is above 0, the task would be display hello number of times, just to see it on the screen. Once I do this, I need to trigger or modify number of times so that I know that I'm done with one iteration. Then I'm going to call it from main. I'm going to say 5 times. Run with F10. F10. So display go. Oh, sorry, I didn't call the message. So here I'm gonna call display again with a decreased number. So decrease first and then execute. Or I can say a num of time -1 equivalent. So go. What's num of times at this point? Num of times is 5. Is it above 0? Yes. Okay, then display. Then call display 5 -1. So F11 again. Now I'm on the second call. Is it above 0? Yes. Call again. So now I'm at the third call. Call again. Second 2, I mean. Oh, I should have did F11. Notice 5, 4, 3, 2, 1. Then it broke out of the chain. So this display right now is a recursive function. I can call it with 10, I can call it with 15. Whatever number I give it, it's going to keep calling itself. If I want to draw it, paint, 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 here's paint. If I want to draw it, we're going to go back to this. Now I'm in the first call. So this would be my first call. And number of times is 5 at this point. So the call came from main with number 5. Then is number above 0? Yes. Okay, then display and call again. So now with F11, I am in the second call. So the call or the execution with number 5 called the same function with the number 4. Then again, F11. So now I am at 3. Then again, F11. Now I am at call 2. Again, I am at call 1. Again, I am at call 0. Is this above 0? No, then it will break out of the loop. Or not out of the loop. It will not execute if. Once it reaches here, you know from functions, AAA, once a function is done executing, it's going to return to the caller, whoever called this function. If I have main with a message and my control, the yellow arrow, is at that message or at that call, once once all the scope or all the code inside this message is done, then the control will come back to main. So we'll come back to the caller. So here, right now, I am at 0. Once 0 is done executing, it's gonna go back to the 1. However, when it comes back to 1 with F10, it's not gonna, when it comes back to the 1, it's done executing. So this one at 1, done executing, so it will come to this. Once at 1, it comes to this, it will also come back to 2, come back to 3, come back to 4, come back to 5. Every time it comes back means it's done executing this line. Every time it's coming back, there is nothing to do. So that's why I don't see anything on the screen. So 1 will come to 2 with no code to execute anymore. This will come back, this will come back, this will come back, and this will go back to main. So now I am at main. If I want to visualize this better, I can say, after you execute this, cout done a number of times. What is current a number? So at current number of times, I call display, and after that, I am done. So if I execute again now, notice how the screen is going to look like. It's going to go with all those calls, just like how we drew it. And then once it reaches 0, it's going to start coming back. When it came back from the 0, meaning when it came back from this, there was this line. So every time it comes back, it's going to display done, 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 done. That's basically it as a concept. Now, how can I use recursive in real life situation? A lot of problems. Now, you need to understand first, any function that you, or any problem that you can solve the way you know, can be solved using recursive. Any looping, any iterating can be solved using recursive. It's not like specific problems can only be solved in recursion. No, no specific problems can only be solved recursively, but some problems better be solved recursively just because they show a good or readable code. Any repeatability or any iterating can be solved either recursive or normal, just like the way you know. You're probably gonna have an ugly code, a lot of data structures, a lot of global variables if you solve it normally. On the other hand, if you solve it recursively, you're gonna have a cleaner code, one function, base case, and a task. So it's gonna look nicer if you solve it recursively. One of the problems that are under educational settings that are simple for students to understand is factorial. How to find the result of a factorial. First, what is factorial? Factorial is, I'm gonna use blue. Factorial, and this is the notation of factorial. Factorial of 5 equals 5 times 4 times 3 times 2 times 1. This is good for finding like possibilities, like how many permutations or combinations of X number of numbers there are. For example, let's say I have set of an lotto, for example. You can either choose 1 or 2 or 3 or 4 or 5, and you need to pick a permutation, meaning how many permutations of this set can I have? I can have 1, 2, 3. I can pick one number only once per permutation, meaning this is one way. Imagine lotto. In a lotto, you can pick only you can pick one number only once. So if I have in a lottery ticket, if this is my set, I can pick this ticket, or I can pick 2, 1, 3, 4, 5. This is another ticket. Or I can pick 2, 3, 1, 4, 5, or another ticket. So how many tickets can I pick from this set? The number of tickets is 5 factorial. Why? Because on the first number, when I want to pick the first number, how many choices do I have? I have 5 choices. I can pick one of 5 choices. On the second slot, or on the second number, how many options can I have? How many choices? The fact that I already chose one number, then I'm left with 4 numbers. So I can pick one of 4. And if you want to compute those permutations, you multiply. You have 5 choices multiplied by 4 for the rest. Now that I picked 2 out of the total 5, then I'm left out with the 3 choices. Now that I picked 3 numbers, so I can only have 2 out of the 5. Then now that I picked 4 numbers already, I'm left off with only 1 number. So the number of tickets is whatever this equation is, which is 5 factorial. So that's how you use 5. That's why we use factorial in real life. Now back to recursive. Let me clean. So if I clean all these and I go back to this, in a normal, the way you know before you learned about factorial, if you want to combine or you want to compute 5 factorial, it's easy. You're going to have a loop. You're going to have a function called factorial 5. Inside your function, you're going to have a loop. loop that iterates from 0 up to the input number. If the user is trying to find factorial of 5, then the loop is going to iterate 5 times. If the user is trying to find 10, then the loop is going to iterate 10 times. And on each iteration, you're going to say, okay, current number, then multiplied by the next iteration is input minus 1 means 4. Then on the next iteration, input minus 1. Then on the next iteration, input minus 1, etc. until I'm reached with the input size, which is 5 iterations, and I return the result. So it's very simple. Yes, you can solve it normally. Yes, it's simple normally, but it is a good example to explain recursion. You might argue, okay, the recursive way is not clearer than the normal way. And I would agree, but in order to understand recursion, let's use this example, factorial. So back to this guy. If this is 5 factorial, then we know that 4 factorial equals same formula. 4 times 3 times 2 times 1. Then 3 factorial, 2 factorial, 1 factorial. So 3, 2, 1. These are facts. 3 factorial is always equal to 3 times 2 times 1. 2 factorial is always equal to 2 times 1. 1 factorial is always equals to 1. So if you notice, there is a pattern. 5 factorial equals 5 times 4 times 3 times 2 times 1. But this portion here equals to 4 factorial. And in 4 factorial, this portion equals to 3 factorial. So I'm finding a pattern here. When I observe this pattern, I come to a conclusion for a general equation, general formula for factorial. I'm gonna notice that with the green, factorial of n always equals n times n minus 1 factorial. This is the general formula, and you should agree based on what we see in our observation. Any number factorial is going to equal to the number itself multiplied by n minus 1 factorial, that number minus 1 factorial. So this is a general formula for factorial. Whenever you need to find a factorial of a number, the general equation is that number multiplied by that number minus 1 factorial. So there is a pattern if I want to implement this in code. Anytime the user calls factorial with a number, then I'm going to use that number and multiply it with a new function call, but decrement by 1. So let's put it in code. Factorial is going to return an int. I'm going to call it factorial, right? This function is going to receive a input. Then I'm going to follow what we just discussed. I'm going to have a base case, and then I'm going to have a task. So in my base case, this base case is whatever is going to break the chain. So in my example, what would break the chain? The number would be positives, right? I'm going to have either from a set of numbers, I'm going to either have 0 of numbers or 1000 numbers. So I'm not going to go negative. So this would be my base case. This is the last thing I'm going to reach ever. Let's choose orange. So I can tell my code, as a matter of fact, I can reach like less than, I can reach 0. So I can tell my code, if you receive a call with a 0, then then you don't need to do any computation. You just return the value 1. So my base case, if an outsider calls this method with an input equals to 0, I would like you to return 1. That's it. No need to call yourself again. No need to do anything extra. If a call comes with 0, return 1. Otherwise, I need you to return, or I'm going to say int l result equals, if that's the case, means the input is not 0, then I need you to multiply a input by call yourself with a input minus 1. So this would be the recursion. Notice the same function. I'm going to receive it with a number, but then I'm going to call it again with that number decremented. So now I'm going to say cout factorial, for example, 5. And what is factorial of 5? Factorial of 5 is here, 5 times 4 times 3 times 1. So if I want to validate, 5 times 4 times 3 times 2 times 1 equals 120. So I should see on the screen 120 because that's the value of factorial. So back to the code, I'm going to run. So I'm here, I'm going to say F11, base case. What is input? Input is 5. So let's draw it while we are running it. I'm going to delete this. And then I'm going to say, okay, there is a call. There is a call that came with the input 5. Let's close this. We don't need it anymore. I also don't need this anymore. So is the input equals to 1? No. Okay, then I should return. Here I computed the result, but I should return it. Right? When someone calls factorial, I need to return some value. And here, this is calling factorial. So this should be replaced by the return of this call, meaning a input times the return of this call. So let's run again. Again, someone called it with 5. Is it equal to 0? No. Okay, compute. L results equal a input times factorial 5 minus 1, so F11. Now I'm in the second call. So I go back to paint. The call from 5 called again with the value 4. Then, is this equal to 0? No. Okay, then call again with a 3. So now I am with the value 3. Again, is it 0? No. Okay, call again. 2. And it's going to be again with 1. Then it's going to be called with 0. So back to the code. 2, 1, 0. Is the value equals to 0? Yes. Then return 1. Now this call, I'm going to do it with green. The call with 0 is going to return the value 1. Return, boom. So now I'm back at the call equals to 1. This returned 1, and I have 1, so 1 times 1. 1 times 1 is 1, return 1. So this call is going to return 1. Return. So now I'm at the call 2, which is here. This will compute A2 times 2 because, oh, sorry, A2 2 times whatever the previous call returned, so 1. 2 times 1 equals 2. So the call at 2 will return 2. Now return. Okay, the call at 3 is equals to 3 multiplied by this previous call returned 2. So now the result is 6. So this will return 6. Again, return. Now this returned 6 and the input is 4. So the result is 4 multiplied by 6 is 24. So this will return 24. Again, this will return. So this call returned 24. 5 times 24 equals to 120. So the call at 5 is gonna return 120. Return. Now result finished computing. So factorial finished executing. It's gonna display 120. So I solved this problem using a recursive method. I could have done it with a loop, and yes, it would be simple, but it's simple for this problem. For other complicated problems, recursive is going to be very simple, and solving it normally with a loop is going to be very complicated. So this is one example of factorial. And another example that the book showed was, what was it? Factorial versus Fibonacci. Fibonacci. Let's see where is Fibonacci in the book. Fibonacci is the book tells you like you can solve a lot of problems, exhaustive algorithms. You can do Tower of Hanoi recursively. You can do quicksort recursively. But I'm gonna do the Fibonacci. Fibonacci, is it in the book? Interesting. Fibonacci is not in this section, but it is important for an interview. In an interview, they they ask you a lot to do Fibonacci recursively. Oh, it is in the book. Focus on problem solving. It's page 1, 2, 3, 7. Cool. So now you have a resource to look at, and I'm gonna do it in front of you too. Before we start, let me explain to you what is Fibonacci. So the Fibonacci sequence, it's a sequence of numbers, just like we have our human sequence, 1, 2, 3, 4, 5. It's a sequence of numbers. 1, 2, 3, 4, 5. It's a sequence of numbers that keeps going. And there is a pattern. And remember, in computer science, anytime you need to solve a problem, you need to figure out the pattern. What is the repetition? What is the pattern? This way, if I figure out the pattern or I figure out the repetition, then I can automate it. If there is a pattern, then I can automate a code. If there is a pattern, then I can repeat tasks in my code using that pattern. So if I want to continue with this sequence, what is the pattern that I follow? Anytime I'm at a number, what is the pattern that I need to follow in order to reach the next number? The pattern is plus the value 1. As long as you're following this pattern, you can keep going with the right sequence. If I break this pattern, meaning if I increment +1 for the first 5 times, then I start incrementing 0.9 or 1.1, then I'm going to break the sequence. So as long as I'm following this pattern, I can automate a code that keeps producing the next value in the right sequence. I'm at 1, add 1, I become at 2, add 1, I become at 3, add 1, I become at 4. So the sequence of numbers follows this pattern. Now with Fibonacci. Fibonacci is a sequence of numbers that looks like this. Etc. So what is the pattern in this Fibonacci? Fibonacci, a guy who figured it out, and he claimed that this is a very important sequence. And later it turned out that it's true. It is actually a very important sequence. And you can see it here, for example, Fibonacci sequence in real life or in nature. Let's go to images. If I want to put these numbers in the smallest space possible, I'm going to get this shape. So imagine you have, well, before we go there, you're going to see a lot of things in nature follow this pattern. This pattern is Fibonacci, meaning here I had 1, 1, then they became 2, like this in a size wise. Let's say 1 centimeter, 2 centimeter cube, then 3 centimeters cube, then 5 centimeters cube, then 8 centimeters cube, then 13 centimeters cube, etc. You're gonna see it a lot. Well, this is not right. I don't think this is right. This is the correct pattern. This is a bunch of sequences in the same time. Like you have one that goes like this, and then one that goes like this, and then one that goes like this in one spot. This, maybe a flower. This is very important because this is how they predict weather. They predict weather by saying, okay, this seems like it's following Fibonacci. So the next time, in 2 days or in 3 days, it's gonna be the next number. So if this is 1, 1, 2, 3, 5, 8, 21, then this number would be the next number in the sequence, and this number would be the following number in the sequence, etc. What is the pattern here? The pattern, if I want to look at these numbers, if I give you a minute, you probably will figure it out. The pattern here is every number is the sum of the previous 2. I don't have any previous 2, so it's 1. Here, I don't have a previous 2. I only have previous 1, so it's 1. So the current number equals the sum of 2. So I'm here at this index. Let's move this here. And then I'm with red, I'm going to say this is index 0, this is index 1, this is index 2, this is index 3, this is index 4, 5, 6, 7, etc. So back to this. At index 0, the value is 1. At index 1, the value is 1. At index 2, it's the sum of indexes 0 and 1. What is the value at 0? 1. What is the value at 1? 1. So 1 plus 1 equals to 2. At this index, at 3, at index 3, the value is the sum of 2, of the previous 2, becomes 3. Then at index 4, the value is the sum of the previous 2. Then at 5, the value is the sum of the previous 2. At 6, it's the sum of the previous 13, the previous 2, 21, etc. So the pattern is, let's do blue. The pattern is fib of n at any n, the fib of n at index n equals to fib. Well, before I complicate it a little bit, let's go back to drawing. Let's take, for example, this example. The fib of 6 is 13. How did I figure it out? Because it's the sum of the previous two. However, the previous two as values are also the previous two, meaning 6 is the previous two, but the previous one is also the previous two. And the one before the previous one is the previous of 2. But also, the previous 2's are also the previous 2's and also the previous 2. So if I am at 6 and I need to find the previous 2, the previous 2 is also Fibonacci of the previous 2. Then the previous 2 is also Fibonacci of the previous 2. So at any index, I can go back and figure out what the value is. So Fibonacci, the general formula is Fibonacci of n always equals Fibonacci of n minus 1 plus Fibonacci of n minus 2, because these are the previous two. N minus 1 and n minus 2. How can I compute their values? Their values is the Fibonacci of it. Fibonacci of n is the previous two, but the previous two are, if I want to find the value of Fibonacci at n, I call Fibonacci. Correct? We agree. If I want to find the Fibonacci number of index n, I call Fibonacci n. Fibonacci n is the previous two. How do I find the value of the previous two? If I want to know the Fibonacci of n minus 1, I call Fibonacci n minus 1. How do I find the Fibonacci of n minus 2? I call the Fibonacci n minus 2, and that will get me the value. What is the, where do I stop? When I'm going back, when I keep going back, where do I stop? I stop at index 0, because it doesn't have previous two. So Fibonacci of 0 always equals to 1. Fibonacci of 1 always equals to 1. Fibonacci of less than, if Fibonacci of 0 and less is equals to 0, and Fibonacci of 1, or Fibonacci of 1 is 1. So basically this is my base case. When I reach 0 or 1, they return the same value. Or some people start the Fibonacci with the value 0. So basically these are a little to the left, meaning Fibonacci of 0 equals to 0, Fibonacci of 1 equals to 1. Let's follow this example because it is simpler for you. As a base case, however, it's doable whether it's this or that. But let's follow the Fibonacci using 0. Starting from 0, 1, 1, 2, 3, 4, 5. The index of 0 is 0, the index of 1. So my base case would be, if someone calls Fibonacci with the value 0, then the value or the result is 0. If someone calls Fibonacci with the value 1, then the value is 1. If someone calls me with Fibonacci 2, I have a previous 2, so I'm going to execute the recursion. If someone calls me with 2, then it is the previous 2. If someone calls me with 1, I don't have previous 2, so I'm just going to return the value as is. If someone calls me with 0, I'm going to return the value of as. Anytime I do have previous 2, I'm going to execute recursion. So let's do it in code. I'm going to call it fib, and I'm going to call it an input. I'm going to have base case, and then I'm going to have a task. So what's my base case? My base case we just agreed. If a input equals to 0, return 0. And if a input equals to 1, return 1. These are my base cases. Anytime I reach these two values, I don't want to compute anything. I don't want to recur anything. I don't want to execute recursion. I just want to return value as is. However, anytime someone calls me with different values, but let's eliminate negative. So anytime it is less than or equal 0. Anytime it's less than or equal 0, I'm going to return 0. So this way I'm protecting my code. If someone calls me with a negative, I'm going to return 0. There is no Fibonacci number for negative. So anytime someone calls me with different numbers, that means 2 and above. Anytime someone calls me with 2 and above, I do have a previous 2. So I'm going to execute. I'm going to say int l result 1 equals, just so we have it clear, I'm going to call result 1 equals, or result minus 1, so you understand it better. I'm going to say L result minus 1 equals fib of a input minus 1. And int L result minus 2 equals fib a input minus 2. Then I'm going to return what? Fibonacci of current number equals the result of minus 1 plus result of minus 2. So return L result minus 1 plus L result minus 2. Do we agree? We agree. So this is the task. Notice every one call is getting expanded to 2 calls. Once these 2 calls are done, then I'm going to return the sum of them, because the Fibonacci of a number is the sum of the previous 2. Save, save, save. Then I'm going to say, okay, display Fibonacci of, let's do 5. What is Fibonacci of 5? I should receive, so 0, 1, 2, 3, 4, 5. So I should receive 5. Execute. Fibonacci of 5. Now I am at the call 5. I'm also going to pin this and this so we can see it in front of us. Right now they are still junk. I didn't reach yet. So let's also delete these. Let's zoom in a little bit. And I'm going to say, this is it. Okay, so now a call came. A call came with the value 5. So is it less than or equal 0? No. Is it equal to 1? No. Okay, then call a input minus 1. So I'm going to click F11. So now I am at call 4. So the call of 5 did the first part, which is calling by 4. Is it equal? Is it equal? No. Call again. So now I'm at 3. Forget about these for now, because they are still not computed. I'm still going in the chain. We didn't return anything yet so that we set this value. So now I'm at value 3. So 4 called 3. And the 3 is going to call 2. And 2 is going to call 1. So let's do it here until we reach 1. Here it is, 1. Is this less than or equal 0? No. Is it equal to 1? Yes, it's equal to 1. Okay, so return 1. Now when I click F11, I'm going to go back to the call 2 with the value 1. So here, this returned the value 1. So this is gonna return the value 1. So F10, here it is 1. Now it's gonna, at the call at 2 is gonna call Fibonacci with -2. So F11, now I'm at 0. So here, this 2 did this first call and received a value. It's gonna call another call of the value 0, and it's gonna return what? Is it equal to 0? Yes. Okay, so return 0. So now I am back to the call 2. 0 returned 0. So now I'm at the call 2, and it's gonna return whatever the result from 1, -1, and whatever the result from -2. So 1 plus 0, which is here, 1 plus 0. So the call 2 is gonna return to 3, 0 plus 1, 1. So return. So now I'm back at 3. 3 from the call of 2 returned 1, which is 1 plus 0. Then it's going to call again, but now with input -2, which is 1. So 3 is going to call again, now with the value 1, because 3 minus 2, input -2 is 1. So now that I'm up to 1, is it equal to 1? Yes. Okay, then return 1. That returned 1. Now I'm back at 3. So the call to 1 returned 1. Now I'm at the call 3. The call at 3 will return to 4, 1 plus 1. The result from A input -1 and the result from A input -2. So 1 plus 1. What is 1 plus 1? 2. So return 2. Return back to the call of 4. Back to the call of 4, it returned 2. Here it is. So let's draw it. From 3, return to 4, the result 1. Now I'm at 4, and I'm gonna call it with a input -2. So 4 minus 2 is 2. F11, is it 0? No. Is it 1? No. Okay, since it is Fibonacci of 2, I need to call it with a input -1, a input -2. Basically, whatever we did here, Fibonacci of 2 is the result of the previous 2. So it is 1 plus 0. So I'm gonna call again. Right now we are at a input 2. So 4 called again with 2. And 2 is gonna call 1, and it's gonna call 0. We know that for sure because we already observed it. So call with 1 and call with 0. Here it is, return. So now I'm back at the 2, and the 2 is going to return 1 plus 0. So 1, sorry, this should be 0. So this will return 1, and this will return 0. 1 plus 0, so it will return 1. So 1 plus 0 is 1, so return. Now I'm back at 4. I'm back at 4, and -2 returned 1. So now I have 2 plus 1, which is, oh, this should have been 2. 1 plus 1 equals to 2. Right? This call returned 1, and this call returned 1. 1 plus 1 is 2. So return 2 to 4, and now I have 1. So 2 plus 1. So 2 plus 1, here it is, 2 plus 1, return it to back to the call of 5. The call of 5 called it with 4 and received 3. So now 2 plus 1, this call will return 3. Now we are at -2. So 5 minus 2 is 3. So now I'm calling with the 3. 3 is going to do the same thing we did earlier, which is similar to all this chain. So here, this called 4 first, and now it called 3. 3 is going to call with 2 and 1. 1 is going to return. 2 is going to call with 1 and 0. Then this is going to return, we know for sure it's going to return 0. And this will return 1 because these are my base cases. 1 is going to return 1 because this is my base case. And 2 is going to return 1 plus 0, which is 1. 3 is going to return 1 plus 1, which is 2. So let's move with the code until we reach that spot. So 1 plus 1, we are at here. 1 plus 1, return 2. Now that I return 2, I'm back at 5. I have 3 from the -1 and I have 2 from the -2. We can validate by showing it here. I want to scroll here. Yep. So I can validate it right there. 5 has 3 from the previous one and has the value 2 from the previous 2. So 3 from the previous one and 2 from the previous 2. So now we return to the caller, whoever called me here, return the sum of them, 2 plus 3. So this is gonna return 2 plus 3, which is 5. So return, boom. Now I'm at 5, display it. It is the value 5. Continue. Now that I did this, I can, for example, call it at index 7. At index 7, it is so 5, 8, 13. I should see 13. Here it is, 13. Fibonacci at index 7 is the value 13. So now I can predict things. Oh, okay, I have records for 3 days of weather, and I see that they are following Fibonacci. Okay, what is the weather in day 6? Oh, if the value of on day 1 it's 1 inch of snow, and then on day 2 it's 1 inch of snow, or sorry, 0, 1, 1, 2. So if at day 1, day 0, if I have 1 inch of snow, 1 inch of snow, then 2 inches of snow, and then 3 inches of snow, then 5 inches of snow, then I know that on the following day it's going to be 8 inches of snow. If we are going, if nothing changes, then it's going to be 8. It's exactly similar to when you have, for example, 2 cups of water, right? If you have 2 cups of water, let's say these are my cups of water. I have 1 cup of water and I have 1 cup of water. This has this much water and this has this much of water. The sum of them is a cup of water that is this amount plus this amount, basically. So the result is the sum of the previous two. So if I have 2 winds, right, in the same vector or in the same direction. If two winds combined, they produce a wind that is sum of the previous two. So any wind, if in a perfect world, any wind moving in this direction is the sum of the previous two winds that came in that direction. Now you can argue that winds were going one this way, but at some point the energy collided and absorbed each other and produced two winds going in the same direction that they became one. So that one, the result of both winds were the sum of the previous two that were going in the same direction. So it's just an example. You can think about it any way you want, but this is basically recursion and Fibonacci. Now the homework is very interesting. The homework is, if I call Fibonacci with 1, it's gonna take a while. See, I didn't get the result. It's loading. Why it's gonna take a while? Because every function call is gonna create two function calls, just like how I saw here. 2 called 1 and 0, 3 called 2 and 1, 4 called 3 and 2, 5 called 4 and 3. So, and every time I go inside the tree, I'm branching into 2. So when I call it with 100, that's a lot of work. When I call it, see, it's still working. That's a lot of work for the computer at 100. So the homework is to do some caching. Basically, notice in here, for example, when I called 4, when we went this way, when we went in this direction at the first time, when we went in this direction, we didn't have anything computed before. We had to compute every step. However, when we reached, for example, this, well, when we came back, for example, to the 4 called 2 again. However, when it reached 2, I had to recompute 2, but I already computed 2. So why to recompute 2 when I already computed 2? I could have cached it. Anytime I compute something that I didn't have before, I can cache it. I can cache it in a map. I can cache it in a vector. I can cache it anyway. I can say, okay, at key, if I want to use the map, at key 3, the value is X. At key 4, the value is Y. At key 2, the value is Z, etc. Or if this is for vector. If I'm using, this is for map. If I'm using a vector, I can say, okay, at index 3, it's equal to X. At index 4, it's equal to Y. At index 2, it's equal to Z. So anytime I am at an index that doesn't exist in my vector, or is not populated in my vector, or doesn't exist in my map, whatever data structure you're using, the concept is called memoization, means remembering previous computations and using them. Caching, if you want to call it, if you want it simple, caching. So here, back to this point, I reached an index or a value that I already computed. So if I had it in my vector or in my map, I could have, instead of executing recursion, I could have just returned the value that I already computed. So in this case, instead of going this path, I could have just said, oh, okay, every time a call comes, check if I have that value. If I have that value, return it instead of executing recursion. Also, if I want to follow I did this, then this did this, then this returned, then this 5 returned, but 5 also executed Fibonacci of 3. When I reach Fibonacci of 3, I executed recursion. However, I already computed 3 here. So when I computed the 3, if I cached it, then anytime I return to 3, I can return the value from the cache instead of executing recursion. So this is the homework, and this is memoization. It's very simple. You use this code that you have in front of you, but add some cache into it. Add some container, add some data structure that says, oh, I input, okay, I have it. Let me return the value. If a input exists, return this value, whatever the value is from your cache. You have a cache. You have a map, key 3, value X, key 4. So if you receive 3, then go to your map and return the pair of that key. The key is 3, its value is X. So let me know, this is the session. This is basically it. Let me know if you have any questions.